All right, folks. So today we're talking about, that's an exciting delay, section 4.3, which is all about the mean value theorem, or at least it's a little bit about it. And monotonicity, all right, which is a fancy word meaning something that's always increasing or always decreasing. And they're bearing the lead a little bit because it's also about the first derivative test. So, what we have from this section, the mean value theorem itself is that if f is continuous on the closed interval AB and differentiable on the open interval A and B, there exists a C in the interval AB with the derivative at C equal to something that looks an awful lot like the difference quotient. And this is just, or rather, Rolle's theorem from last time is a special case of this, where f of b equals f of a, because in that case, this fraction here equals 0. And remember, it had the f of b equals f of a up there, right? But even if those two aren't equal, even if the endpoints don't give you the same thing, then you can still find some point here in the derivative. Right? So for monotonicity, we have a rule that says if f prime of x is greater than 0 for all x in AB, f is note f, not the derivative, the function itself, is increasing on AB, and if the derivative is negative for all x on an interval, f is decreasing on AB. Right, so that's the monotonicity part of it. Right? And the first derivative test part of it says if C is a critical point and f prime changes from positive to negative at C, then f of C is a local max. If f prime changes from negative to positive, then the function has a local minimum at C. Right? So that means that if we want to figure out things about local maxes and minimums, we can find all of the critical points and check what f prime is doing before and after those critical points, and then we automatically know whether it's a local max or local min. Right? So now we can actually figure out whether or not a critical point is an extremum, a local extremum, without having to just graph it. right? We can tell absolute extremum by plugging in and there's going to be only one biggest and only one smallest. But that doesn't tell us whether locally there's one of those small hills at one of these places. That's what the first derivative test is for. So let's get into some problems, and we'll start with the mean value theorem. So let's verify the mean value theorem on 0 to 2 pi. Right, and what this means is, well, let me finish writing the problem first. That might help. Right. So what this means is, as long as we know we're continuous and differentiable, which we do, we're the sum and composition of a handful of continuous and differentiable functions, then we want to show that, so this translates to find C in 0 to 2 pi, where f prime of C equals f of 2 pi minus f of 0 all over 2 pi minus 0, right? So that's taking this statement here and showing that it's true by finding the C that it says exists, right? So the theorem just says that there's one that exists. It doesn't tell you anything about what it is. So we can verify a theorem like that by finding at least one of those C's where it exists, right? But to do that, we have all of these pieces, so we just need to figure out what the derivative is. So the first step is going to be to find the derivative. So the derivative of x is just 1. Now this piece is going to require the chain rule, right? So the derivative of the outside is cosine. Then we want to plug the inside in, right? So just to be clear here, the outside is sine of x. The inside is 2x, right? So we want the derivative of the outside with the inside plugged in times the derivative of the inside, right? So we're going to get 1 plus 2 cosine of 2x. Just so it's here. As a reminder, that's the derivative there, and that's the derivative there. Right, so the derivative of the outside with the inside plugged in times the derivative of the inside. So we get this guy as our f of x. And so now we want to solve for C, where 1 plus 2 cosine of 2c, right? So this is f prime of C equals f of 2 pi minus f of 0 all over 2 pi minus 0. Now we can simplify this a lot. 2 pi, sine of 4 pi is just 0. 0 is still 0, and sine of 0 is 0. So this is just going to be 1. Okay. Whew, that's looking a lot simpler than when we started. So we're going to subtract 1 from both sides to get, we're looking at cosine of 2c equals 0, which we divide by 2 on both sides to get cosine of 2c equals 0. That's one of our quadrantal angles. Whenever you have a sine or a cosine equaling 0 or plus or minus 1. And we remember that this happens if 2c is equal to pi over 2 plus 2k pi, or if it's equal to 3 pi over 2 plus 2k pi. Right? Because remember, whenever you're solving trig equations like this, once you get to this step, you take the entirety of the inside here and set it equal to the full list of possibilities. Right? And that's because of this next step, which is when we divide by 2, we have to divide everything by 2. So it's pi over 4 plus k pi, because we've divided that 2 out. And it's 3 pi over 4 plus k pi, because we've divided everything out. So now we have the trick of figuring out which of those solutions are in here. Well, technically we don't. I'll talk about that in a second. But just for the practice, because it may have been a while for folks. Right? If we want solutions in 0 to 2 pi, well, we take k equal to 0, and we get these two. I know that if k is negative, we're going to be a negative number, so I don't have to worry about that. When k equals 1, we get 5 pi over 4 from here. Right, this is k equals 1. These are both k equals 0. K equals 1 on the other one gets us 7 pi over 4. K equals 2 gets us 9 pi over 4, and that's too big. Right, and I know the rest of them are just going to get bigger. Right, so our solution set is these 4 numbers. Right, now we were just trying to find a C. Right, we were trying to find a C that lives in there where this is true, so we weren't actually trying to find all of them. Right, the moment we got to this step, we could have said, pi over 4 works, we're done. C is pi over 4, that's a solution to that. The mean value theorem doesn't say how many C's there are. It doesn't say that there's exactly one. It doesn't say there's more than one. It just says there's at least one. Right? So in this situation, because of why we were solving that equation, we can just choose any of those values that work. But if we were trying to find all the solutions, this is what we have to do. Right? Let's see. Let's do another problem. Determine where f of x is increasing and decreasing, and classify local extrema. Right? Classifying local extrema is a fancy way of saying figure out which crit points are what type of extrema. Right? So, all of that, increasing, decreasing, and classifying local extrema, have to do with our derivative values. So first I should tell you what f of x is. That might help. Right, but in problems of either of these types, if you are either trying to find all the increasing places or the decreasing places, or trying to classify local extrema, or both, like we're doing here, then you're going to want to look at the derivative. And in fact, a problem like this is kind of nice, because while it looks like it's two different problems, right, there's the increasing, decreasing, and the classifying local extrema, you have to do the exact same work for both of them, down to a T. So all of the work we're going to do is the same work you would do if you just needed to find increasing or decreasing, or if you just needed to classify local extrema. All of it's going to be the same. Right? So, and the first step of that is going to be to take the derivative. So when we take the derivative, we get 3x squared minus 8x minus 16. Right? We take the power down, and then we subtract it by 1. Right? Same here. And then this is linear, so we just drop the x. Right? So the next thing we need to do is we need to figure out where the zeros are, right? If while we're trying to classify local extrema, that gives us the critical points. If we're trying to do increasing and decreasing, that tells us the places where it will possibly change, right? So the critical points, well, it doesn't exist there's nowhere where it doesn't exist. So we don't find any of those. So we need to look at f prime of x is equal to 0. That looks to me like a quadratic, which means we can either try to factor to use the quadratic formula. Factoring is trickier when you don't have a 1 here. That 3 is causing things to be more complicated than they might otherwise be. So I tend to just jump straight to quadratic formula if there's not a 1 there. There's no reason not to try to factor it if you know the tricks for it. There are certainly a number of them that work fine, but for today we're going to do the quadratic formula, right? So that gets us negative b is positive 8 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this is 8 plus or minus the square root of 64 plus 192 all over 6. 8 plus or minus square root of 256 over 6. Now, simplifying that square root is often the trickiest part of dealing with the quadratic formula, right? It's one of the reasons why, if you can factor it, that's often a nice thing to try to do first, because if you could factor it, then you're going to have to simplify that square root a lot. But this one's not too bad, because I noticed that 256 is a power of 2. And even better, it's an even power of 2. So I know this is going to be 8 plus or minus 2 to the 4th. Right, so that is for the plus and for the minus. So we get 4 and negative 4 thirds. Right, so 2 to the 4th is 16. Yeah, okay, so those are our critical points. And so the next thing to do is to build a number line, put our critical points on it, and then, again, regardless of whether we're doing increasing or decreasing or classifying local extrema, we need to know whether f prime of x, whether the derivative of f is positive or negative in these various places. And the way we do that is by picking any value we want from each of the different categories, right? So for here, I need to pick a value that's less than negative 4 thirds. So I'm going to choose negative 2. That's supposed to be f prime, right? Just because that seems like a nice smallish number that'll be pretty easy to plug in that is less than negative 4 thirds. Right, so this is going to be 3 times negative 2 squared minus 8 times negative 2 minus 16. And, oops, that needs to be squared. So one of the things, this one's not too bad to plug in and actually do that algebra for. But we're going to do a lot of problems like this. And one of the talents that it would be good to cultivate when you're doing problems like this is figuring out whether it's positive or negative without doing all the work. I don't actually care what number this is. The number that this is means nothing to me. What I care about is whether this is positive or negative, right? So one of the things that I notice is that this is going to be positive 16. This is going to be negative 16, so they cancel each other out. And then this number right here is positive because the square gets rid of the negative, right? I'm going to choose 0 here because 0 is always the number that makes polynomials the easiest, right? It's just the linear term, so this guy's negative. And here I have to choose a number bigger than 4 to be the piece from up here. So, you know, I'm going to choose, for funsies, I'm going to choose 10, right? Because it doesn't have to be the closest thing. It just has to be something nice, right? And that one's pretty easy to do. I know how squares work, right? If you are multiplying something by 10 or a power of 10, you just put that many zeros after it. So I know it's going to be 300, because there are 2 zeros, minus 80, because there's 1 0, minus 16. And I could work out what that actually is, but I don't really care. 300 minus 80 minus 16 is definitely going to be positive, right? It doesn't matter what it is exactly. I just care whether it's negative or positive, right? And there was nothing special about the numbers that I chose here, except that they lived in their individual pieces, right? I could have chosen negative 3 for here. I could have looked at f of negative 3 or f prime of negative 100. Right, I could have chosen anything here. I could have chosen f prime of negative 1. I could have chosen f prime of positive 1. I could have chosen f prime of 2.5. That seems a little bit silly. It's kind of hard to deal with fractions when you're plugging it into a big polynomial. But I could have chosen any of those, right? And here I could have chosen 5. I could have chosen 4.1. Again, that seems kind of silly, but I could have chosen it. I could have chosen 1,000 if I really felt like it, as long as it was a number bigger than 4, right? So those are the only requirements for what you choose there. It's whichever one you think is going to be easiest to plug into the function, right? I could have chosen, if this were a function with trig, if this were a function that had trig functions as a part of it, maybe I chose 2 pi. Right? I know that's going to be bigger than 4, and maybe that would be a nice thing to plug in and help me get some simple values, right? So whatever I want to plug in there is fine, whatever makes it easiest, as long as it lives in the categories in between your critical points, right? So before we said increasing is when the derivative is positive. So that's going to be from negative infinity to negative 4/3. And that union means you've got 2 pieces coming, or you've got another piece coming at least. 4 to positive infinity, right? Decreasing is going to be where f prime is less than 0. And we figured that that's between negative 4/3 and 4. Right. And then we know that f of negative 4/3, let's check this real quick, right? We said that if it changes from positive to negative, then it's a maximum, right? So we were positive over here, we passed over negative 4/3 and we became negative, so that means that this is a local max, and f of 4, we started off negative, and when we moved over 4, we became positive, and that was our clue that we had a local minimum, right? So the process for both of these types of problems are find the critical points, put them on a number line, figure out whether the derivative is positive or negative in between them, and then use the rules that we have. All right. All right. So let's do one more. I might talk over a little bit of the algebra without writing it out, just for time's sake or space's sake mostly. We're going to do the same for f of x equals 2x squared over 3x plus 6. Right? So, first thing we need to do is find critical points, which means we need to take the derivative. This is a quotient, so I want low and high. And I want d low, and I want d high. So f prime of x is going to be low d high minus high d low over the square of low we go. So we can simplify this a little bit. Go ahead and factor that stuff up top. I have an inkling it might come in handy. Right? So there's our derivative as factored as we can get it. So we need to know where it doesn't exist. Right? And that's going to be exactly where 3x plus 6 squared equals 0. Right? Because denominators can't be 0. So that's the same as 3x plus 6 equaling 0. And that's x equals negative 2, right? We subtract the 6 from both sides, and then we divide both sides by 3. So that's going to be one of our critical points. And then we need to say f prime of x is equal to 0. So that's going to be the same as the numerator equaling 0. Right, and since we went ahead and factored it, we can split that off. That's 6x equaling 0, or x plus 4 equaling 0. So x equals 0, and x equals negative 4 is our 3 critical points. All right? So, now we need a number line. Right, we put our 3 critical values on there. Now we need to pick a value from each of these. And so what I chose from this first one is negative 5. All right, so I chose negative 5 from this section. So here's, I mostly wanted to do this one to sort of get some practice in with figuring out positive or negative. One of the things about this function is that it doesn't matter what x is, this is always positive, right? When you square a real number, you're always going to get a positive number out of it. So I don't have to plug it into the whole thing. I can just plug it into the top. Right, so this is not going to be equal to. Notice I didn't put equal signs here. But it's going to be positive or negative. Let me move this so we have enough room. Oops. Right, again, I want to stress, I'm not saying these are equal. But part of the thing with doing this process is that I do not care what number f prime of negative 5 is. Nobody cares what that number is. It means nothing. It's useless. It's pointless. The only reason we're doing anything with it is we want to know whether it's positive or negative. And the denominator of that function is never going to change that. It's always going to be positive, so if the numerator is negative, a negative divided by a positive is negative. So it's the same thing as the numerator. if the numerator is positive, a positive divided by a positive is a positive, so it's going to be the same thing as the numerator, right? So I am not saying these are equal, but they're going to have the same sign, right? And so here we have a positive number times a negative number, and this is going to be a negative number, so all in all, this is going to be positive, right? And that's all we care about. We don't care what the number is. We don't care what the value is. We just care whether it's positive or negative, right? So for this one, I'm going to choose -3, and I'm going to do the exact same trick because I still don't care about the denominator, but I'm going to plug it in to the numerator. And notice that while we have a positive and a negative again, now this guy, 4 minus 3, or -3 plus 4, is positive. So a positive times a negative times a positive is going to be negative. All right. Next, I'm going to go ahead and do -1, because I don't want to deal with fractions. All right. So f prime of -1 is going to be the same sign as 6 times -1 times -1 plus 4. Again, we've got a positive times a negative times a positive. So that's going to be negative. And f prime of, here I'm going to choose 1. It's going to be 6 times 1 times 1 plus 4. And here we have a positive times a positive times a positive. So we're going to have a positive here. Right? So this tells me that we're increasing from -infinity to 4 and from 0 to infinity. Right? And we're decreasing from -4 to -2 and then -2 to 0. We have to be careful. We can't include -2 because -2 isn't in the original domain. Because a function can't be decreasing in a place where it doesn't exist. Right? So that's why we leave that hole there. And f of -4 goes from positive to negative as it hops over -4. So that, I believe we said, was a local maximum. You might can tell I don't remember those very well. F of 0 is a local minimum. And -2 isn't actually an extrema, right? It goes from negative to negative. It doesn't change when it hops over -2. And so -2 is not actually an extrema, right? It's a critical point. It is a critical point, but it's not an extrema because not all critical points give us extrema. And this is a case of one where we have a critical point at -2, but there's not an extrema there. Right? So next section, the basic idea of next section is what if we did all of this stuff, but for the second derivative instead, what does that tell us? And it turns out it doesn't tell us increasing and decreasing, but it does tell us something very similar. So we'll be talking about that next time.